All right, so for example number 5, what we're going to do is just like example number 4, except now we're faced with a piecewise function. And so for any x value less than or equal to 1, we evaluate at 5 minus 2x squared. And so we're going to look at the boundaries for that first. And so the boundaries for that one is just infinity and 1. So 1 might be a point of interest. And so those are the boundaries for the first half of the function. So then we just go through the process and take f prime here, remembering that it's for all x values less than 1. And then when we take the derivative, remember the first step is to look at the intervals and then the endpoints and then look at f prime set equal to 0. So when we take the derivative, we get f prime equals negative 4x. Solve for the 0 and we get x equals 0. So our possible critical points may be 1 and may be 0. Those are where we're going to look for the x values. And so then the next step is to remember that this is for f prime, but here technically we kind of have two f primes. So remember with the critical points, we're looking for x values that we plug into the original f of x, and we just have to remember that there's a first half and a second half, at least in this scenario. So now we're going to take a look at the second half of the piecewise function, which is going to be x plus 2, and by definition of the piecewise function, we're interested in 1, comma, all the way up to positive infinity. And so 1 is probably an endpoint that might be a point of interest, and we'll talk about that in a second. So then we go through and we take the derivative of f, and we get that f prime equals 1, and so f prime does not equal 0 anywhere. Now, one thing I kind of skipped over is that both f primes are defined at all points in their domain, so there is no place where f primes do not exist. So we really only technically have two critical points, all right? And so what we're looking at is when x equals 0 and when x equals 1. And so what we need to do is take those x values and plug them into the original function. And here's an interesting thing. It's a piecewise function. And so when we look at the piecewise function, both 0 and 1 are plugged into the first equation. So when I do f of 0, I'm going to use the expression 5 minus 2. So I get 5 minus 2 times the quantity 0 squared. And so that just gives me 5. So on our function, we have the point 0, comma 5. Next, on our function, we evaluate it at 1. Again, it's the same expression. And so when we plug that into the equation, we get 3. So we have 2 points of interest, 0, comma 5 and 1, comma 3. Now, if we just looked at that information, we would probably guess that 0, comma 5 would be the max and 1, comma 3 is a minimum. And that's true, they are mins and maxes, but what we really want to know, are they extreme or are they relative locals? So is it a local min and max, or is it an extreme min and max? And so I forgot, that's supposed to be negative infinity, but I penciled it in there. We didn't talk about what does the graph do as it approaches infinity. Well, this is what we call end behavior, and so it's like we probably would take a limit. So when we talk about the end behavior of a function, usually there's like 3 scenarios. Either it goes to infinity, negative infinity, or if there's a horizontal asymptote, we might run into a scenario, and likewise if there's a vertical asymptote, we might run into an issue. And sometimes if we understand what vertical and horizontal asymptotes are, that'll help us out. But a vertical asymptote always occurs usually when the expression itself is undefined. In other words, you have an expression of x in the denominator, and that creates a vertical asymptote. For example, 3 could not be an x value, so there would be a horizontal or a vertical asymptote at x equals 3. Horizontal asymptotes occur when we have rational expressions that have polynomials as numerators and denominators that have the same power. And so when we think about the limit of this function as it approaches infinity, when we plug in a really big number for x, both the numerator and the denominator have a tendency to grow at the same rate, and then all other terms become insignificant. And those terms, the x cubed on the top and bottom, get multiplied by 3 and 5. And so the x cubes kind of cancel out. And so we'd have a horizontal asymptote at the ratio of the leading coefficients. But you know what? As I look at this function, I don't have rational expressions. I don't have a domain restriction like a 0 in the denominator. So now I'm just going to graph it. And so when I go to graph it, I'm just basically, remember, we know that there's a min and max, right? When x equals 0 and x equals 1. But what we're trying to determine is it the extreme minimum? Is it the extreme max? And there's a second derivative test that we could do, and a first derivative test actually that we could do that would help us out with that. But I haven't quite covered that yet. Let's just look at the graph and see. So what I'm going to do is I'm going to graph this function, and I want to graph it as a piecewise function. So when you graph a piecewise function in your graphing calculator, you first enter in the first expression, and then you have to enter in the parameters. So we're looking at the expression 5 minus 2x squared when x is less than 1. So what I'm going to do then is I first put in parentheses the expression, and then I put the restriction. In other words, x has to be less than or equal to 1. Now, that's the first part of the function, so I enter in the plus symbol, right? And then I put the second part of the expression, which is x plus 2, followed by the domain restriction or boundary of that second expression. And so once you do it that way and you hit graph, and I've got to make some adjustments so that it'll zoom in. Here we see, hold on, let me hit the graph. Let me go back. Okay, so we have the expression, then the restriction plus the expression. Okay, yeah. Here we see when x equals 0, there seems to be a relative max. And when x equals 1, there appears to be a relative min. And like I said, there were no vertical asymptotes. There were no horizontal asymptotes. So clearly the graph approaches positive and negative infinity based on the end behavior of the function. So we do have a min. We do have a max. But they're not extreme mins or extreme max or a global min or a global max. And usually, you know, I'm throwing a lot of terms, but textbooks use different terms. So when we look at the maximum value when x equals 0, that's good. That tells us something about the graph and the behavior of the function. When we look at the minimum value, that's good as well. So our two critical points were helpful. They gave us some relative or local mins and maxes, and that occurred at x equals 1 and x equals 0. And those corresponding y values were 5 and 3. Does anybody have any questions?